All right, last time we started section 3.4, we were looking at multiplication of whole numbers. And I believe we were at the part of taking a look at the properties. Is that right? Yes? Okay, great. All right, so there are some of these that have similar properties, or at least similarly named properties, inside of the addition section. So some of these definitions are very similar. The first one is the closure property. The closure property says that for all whole numbers, if you multiply two whole numbers, you get another unique whole number. Which, of course, you know to be true. You never multiplied two whole numbers and got a fraction or a decimal. Always just another whole number. The commutative property also works with multiplication, which means that the order of multiplication doesn't matter. So multiplying 2 times 3 is the same as 3 times 2, which is good news for us because it makes flashcards a lot easier for kids, right? You already learned most of them by the time you get to the bigger numbers. The associative property talks about grouping numbers together. So A times B times C, multiplying the A and the B together first, or the B and the C together first, will yield the same result. It is important, like we had on the additive identity, to recognize that the following is a multiplicative identity property. It says multiplication at the top in the purple, but just drawing your attention to it, because the additive identity is what number? What number do you add to things and it doesn't change? 0. The additive identity number or element is 0, but the multiplicative identity is the number 1. So for all whole numbers, whoa, I'm on the wrong screen. I thought it was over, there I was, I just pushed the button. Okay, there we go. For all whole numbers, A, when I multiply by the number 1, it doesn't change the value. So A times 1 is the same as 1 times A, which is A. So the multiplicative identity. And so those are all the ones we basically had before. We had 4 identities in addition, and they all failed in subtraction. So we have these 4 same identities that are with a little bit of variation in multiplication. And then we have 2 new identities in multiplication as well. We have the multiplication property of 0, just saying that when we multiply by 0, we get 0. It's quite the wind out there, isn't it? Howling. But we also have the distributive property now, and the distributive property actually works over addition or subtraction. And the cool thing is that it in fact combines operations. So every other property that we've had has been about one single operation, and this one combines the operation of multiplication with addition or multiplication with subtraction. And you see it going across the parentheses, something like this. AB plus or minus AC. So we're going to run through really quick an example where we just identify what property is being used. Some of them are direct and easy and straightforward, and others of them take a little bit more looking carefully. So take a look at A. What property do you see used there? It could be the identity property, except the identity is not 0. Yeah, so it's the multiplication property of 0. How about B? Everybody wants it to be associative because you see parentheses. Look more carefully. It's commutative, you're right. Associative has to do with changing the parentheses around what numbers they're around. This didn't do that. The parentheses are still around the same numbers, 4 and 3, but the 4 and 3 switched places. So that makes this the commutative property. I know we're not all good at spelling, but commutative is kind of a sticking point for me because usually when people change it, they change it into another word that's really a word, like cumulative or commutativity. Like, that's not the right word. What do they change it to? Communicative. I get that one. That's a disease, by the way. Communicative? Yeah, that's not what we're talking about, okay? So just be careful in the spelling of that one because typically when we alter it, we turn ourselves into another word. We don't want that. How about C? That's associative. Don't abbreviate that one. Just saying. How about D? That's the identity, and we're going to be careful to write on that one specifically that it's the multiplicative identity because it really is different than the additive identity, whereas the associative property is just the associative property in either situation. It works the same way. E and F. Let's do E. Got lots longer problems with E and F. What does E look like? It's the distributive property. And how about F? Can you tell? It's kind of a funny one. Would it be what? It is also distributive. The funny thing is that we're taking the number 1 plus 2 and we're distributing it. So you see the 1 plus 2 showing up times 3 and the 1 plus 2 times the 4. But it's still a distributive property. All right. Let's take a look at an example. JJ claims that the following is true by the distributive law where A and B are whole numbers. 3 times A times B equals 3 times A, 3 times B. How would you help him?
He's saying that the distributive law applies to this.
Yeah. Okay, so you have the right idea. Let me reword slightly but you're on the right track. So what I think you're saying, Kayla, is that in this problem there's no addition, but the distributive property, as it's stated, has addition. So if this said 3, like an A plus B here, then we would have what he's describing, but there's not a plus. Does that sound okay? Okay, so that's definitely true. So one thing to talk about is that the distributive property is multiplication over addition or subtraction. Not over more multiplication. Right? So what if he says, okay, but why can't it be over multiplication? I mean, it works over addition, it works over subtraction. Why can't it work over multiplication, or why doesn't it work? What could you do to show him why it didn't work? Any thoughts? Yeah, okay, so what you could do is to show him that this is all multiplication, like you said. So if you had 3 times AB and you wanted to do something with a property that's about all multiplication, you could regroup your parentheses like this. To see that? And that's a property that we have. It's the associative property. And that might be enough to show him, hey, look, there's that 3A that he's wanting to say here, but the only thing that's left now is B by itself. It's not 3B, right? Can you think of a super concrete way that you could show him why this doesn't work?
I feel like numbers for A.
Yeah. you could actually use an example with some numbers. So you could leave the 3 the same, but just give me some numbers for A and B instead. And we typically like to not use things like zeros and ones because sometimes things are true for zeros and ones that are not true in general. So let's make up something else. 2 and 3. Awesome. And so you could show him that if he does it with order of operations, this is 3 times 6, and then 3 times 6 is 18. But if his idea is correct, then he should be able to rewrite it like this, right? 3 times 2 is 6, 3 times 3 is 9, and 6 times 9 is 54. And these two things are not equal. Not only that, but if you'll notice, they're exactly 3 times too big. Because 54 is 3 times 18. That's exactly the one too many 3's that got involved along the way. Yeah, so there's lots of things we could say to him. If the first one works and he's like, oh, yeah, I just forgot it was an addition, then you're probably good to go. So don't go explaining more than you need to a child sometimes. But if they're still struggling, you need to think about what else could I say? What other approach could I use? Maybe I need to make it very concrete and we could have a different discussion. So those are some different options.
I tutor middle school math, and sometimes I just have to say, forget everything. Just think about it this way.
Yeah, I mean, that's sometimes how it works. So, yeah, I agree. All right, so there's another part of this chapter, this section of this chapter, where we're going to talk about what happens when we repeatedly multiply numbers together, as opposed to necessarily repeatedly adding them together. So these are actually where we're going to talk about our properties of exponents. So to start with, an exponent is defined as a to the n, which is a times a times a, all these a's multiplied together n times. And for a rational number a, we call a the base, and a natural number n, the n is called the exponent. And I suspect you remember most of these. So we're going to fill them in with what the properties say. And then I'd like to show you a justification for why the properties work. So if you have a to the m times a to the n, do you remember how you can write that with a single base? Right, we add the exponents. And if when it's multiplication, we end up adding the exponents, what do we do when it's division? Subtract the exponents. Now, 3 is different because it's a to the m to the n, you only have one base. So it's an exponent raised to an exponent is what you're actually seeing basically there, right? A base and exponent raised to an exponent. So what are we doing with m and n on this one? Yep, we multiply them together. And then the last one looks and feels like it's some sort of a distributive property. And we write a to the m, b to the m. And again, this is one of those things where it's important to notice that these a is multiplied by b that this works. If a were added to b, it doesn't work. But multiplied, it does. All right, so let's take a look then at why these theorems work. And we're going to just rewrite them on the next page as to what they are. So this is m plus n, m minus n, and then I'll keep going. I've got m, n, and a to the m, b to the m. Okay, and then we're going to go back and we're going to justify. Okay, so this is proof by example, which means it's not really a proof. But I am trying to justifying it with an example problem. So we're going to do the example problem of a to the 3 and a squared. And we have an expectation based on the rule that we've just said about this exponents, but I want to show you that it really works. So what in the world does a to the third mean? Fantastic. A times a times a. And what does a squared mean? A times a. So that's a cubed, a squared. How many a's are there? 5. So we can write that as a to the 5th. And if you compare the exponents, where we started, 3 and 2 to become 5, 3 and 2 become 5 by addition. So it added the exponents. The next one, another example problem. We're going to write a to the 4th over a to the 1st. What is a to the 4th? A times a, 4 a's, right? Divided by a to the 1st, which is a. And what can I do? Yeah, I cancel or reduce by a factor of a, which leaves me with a times a times a, which looks suspiciously like a to the 3rd. You're right. And if we look at this 3 and this 4 and this 1, we can see that 4 minus 1 is 3. All right, the next one. A to the 3rd squared is what we're going to do. So I have a cubed squared. So a cubed means a times a times a. And then squaring that means doing it twice. How many a's does that give me? 6. And again, how do I get 3 and 2 to become 6? I multiply. Yep. Last one. We're going to do AB cubed. And of course, cubing means multiplying it by itself. So it's AB, AB, AB. And then what property or properties allows me to regroup the A's all together and write A, and then regroup the B's all together and write B, B, B? What am I doing? I should be doing commutativity and associativity, right? So in some of those cases, I had to switch the order in the A and the B to get all the A's to the beginning, all the B's to the end. And I also had to regroup the pieces that were actually together. But of course, that gives me then A cubed, B cubed, as we expected. All right, so let me do this one last example. I'll post the rest online because this is one more example is a good stopping spot. Example number 4 uses those properties. Okay, so we're going to simplify the expression. You need to make sure of one thing that sometimes we're not always careful to do. All these properties hinged on the fact that the bases match. They're all A's, right? So if bases don't match, I can't go adding exponents together. Like I can't say 2 to the 3rd and 3 squared somehow becomes 6 to the 5th. No, I can't do that. There's no way to combine that in an exponential way unless the bases match. So either the bases match or I have to see if I can get them to match. So on this problem A, they all match. They're all base 5, right? So the properties I have will hold with the base 5. And then how am I going to combine those exponents? I'm going to add them, right? They should be all added together. So 10 plus 2 plus 4, which is 16. So B is exactly what I was warning against, right? It is. Because they are not all matching. And I need to see if I can get them to match. And there's a couple of different ways that I can. So let me show you options for how you could do this. Option number 1 is that you could take the number 6 and break it into 2 parts. What is 6? 2 times 3 or 3 times 2. And this tells me it's to the power 4. Then I have 2 cubed times 3 cubed. And then what can I do with the 2 times 3 to the 4th? property would be useful? The one that looks like distribution, right? Property number 4. The one that says that I can apply the power 4 to each of my individual bases. So 2 to the 4th times 3 to the 4th. And I have 2 cubed times 3 cubed. So now I have some matching bases. Now they don't all match, but the ones that do match can be grouped together, and the other ones that match can be grouped together. So I can match my 2's, and I'll get 2 to what power? To the 7. And then I can match my 3's, and I can get 3 to the 7th. And this is one legitimate answer with one legitimate strategy. Let me show you option number 2. Instead of taking 6 and breaking it down, what I could do is I could take the 2 and the 3 and group them together. The reason I can do that is because they have the same exponent. So it's kind of like I'm undistributing or factoring out that exponent. Right? If I'm allowed to distribute it in, I'm allowed to pull it back out. And if I do this way, 2 times 3 is 6, so I have 6 cubed. And then I would end up with 6 to the 7th. Now, these are just 2 variations of the same problem. When we get into chapter 4, we're going to be looking specifically at ways of doing prime factors, and we will prefer the first one because 2 and 3 is more broken down than the 6. But for what we're doing right now, we don't care. Either of those options will work. Okay, so I will post a video finishing 3.4, all right? If it's a portion of a video that I tell you need to start at a specific place, you don't need to watch the first part of it or whatever, just pay attention to that. And then this homework will be due online. I'll send you all the due dates and everything, but it'll be due online on Monday at 1. Well, at Monday at 12, since 12 o'clock is your time. I don't mean spring break Monday. I mean the Monday after that. Nothing's due during spring break. That's never the expectation. So the Monday after that we have decided we're not coming to school. Yeah. You can for now, yes, and I will set up, at least starting later then, we'll set up some hours and things like that online and how to do that. But yeah, for this assignment, I won't have started anything because it's just during spring break. But if you do need help with any of the questions, feel free to email. Feel free to attach a picture of your work to your email to give me a reference point. That sometimes is helpful to me to know what you've done or how you've thought about something so far. And it's also helpful for you to just not be like, I don't understand this problem and say nothing about what you've thought about before, because I might be telling you information that you're like, I already knew that. And I'm like, oh, well, I didn't know. So give me some background about where you already are in the thinking process so that I can pick up on that part and then, okay? Have a great spring break.